Hello everyone. In today's lecture, we are going to learn about an important and useful concept in the world of vectors, and that's called the dot product. The dot product is about the multiplication of two vectors. So far we have learned about the addition of two vectors. We've learned about multiplying a vector by a scalar quantity. However, we haven't dealt with multiplying two vectors. When we multiply two vectors, it's called the dot product. We will learn what the dot product is and how to calculate the dot product. We will look at the formula for it, and we'll work perhaps on an exercise on finding the dot product of two vectors. Here are the topics that will be covered in this lecture. We'll first learn how to find the dot product of two vectors. We will look at the formula first and then how to use that. We'll learn how to find the angle between two vectors. And finally, we will see how to use the dot product to determine if two vectors are orthogonal. We have to, of course, understand what orthogonal means. Therefore, we will first explain what we mean by orthogonal and then how to use the dot product to determine if two vectors are orthogonal or not. Let's first understand what we mean by the dot product of two vectors. The word product implies multiplication. Therefore, dot product involves the multiplication of two vectors. Now, whenever we multiply two vectors, the end result is a scalar quantity. In the next slide, we will learn the formula to calculate or to perform the dot product and see how we come up with a scalar quantity as a result of that operation. Here's a formal definition of the dot product. As the name suggests, again, dot product involves the multiplication of two vectors. If we are given two vectors, one of them is a v, the other one is a w, and each of them is represented in terms of the unit vectors I and j, then the dot product of v and w, written as v dot w, will be multiplying the horizontal components of the two vectors, therefore a1 times a2 plus b1 times b2, b1 and b2 being the vertical components of each of the two vectors. Right? When we add these two products, a1 times a2 and b1 times b2, we will end up with a single numerical value, which is a scalar quantity. Now let's work on an example of finding the dot product of two vectors using the formula that we just learned. The formula was v dot w will be equal to a sub 1 times a sub 2 plus b sub 1 times b sub 2. Now it's very important to identify the values of a sub 1, b sub 1 and a sub 2 and b sub 2 correctly in order to work through it to get the right answer. Now, it's best to write out the general form of a vector in terms of I and j. It's v equals ai plus bj, correct? So between the two terms here, ai and bj, we have a plus. Let's look at the vectors that have been given to us. It says if v equals 7i minus 4j and w equals 2i minus j, find each of the following dot products. Now the vectors over here, they have a minus sign in between the two terms, correct? Therefore, we should first rewrite them in the general form, rewrite them matching the general form, and that will help us identify the values of the components A's and B's correctly. All right, so if we have to write 7i minus 4j with a plus sign, then this is how it would look like. It would be 7i plus negative 4j. Therefore, A would have a value of 7 and B would have a value of negative 4. And that would be A sub 1 and B sub 1 if that is the first vector in the dot product. As far as W is concerned, let's rewrite the same for W. Again, the general form is AI plus BJ. So let's match it now. So it's 2I plus minus 1j. So A will have a value of 2 for vector W, and B will have a value of -1 here. All right. So now that we have identified our A1s, B1s, and A2s and B2s, we can go ahead and plug in the values in the formula for each of these dot products. So V dot W is A sub 1 times A sub 2. Let's see if we have plugged in the values correctly. A sub 1 is 7 and A sub 2 is 2. So A sub 1 is a 7 and A sub 2 is 2. So 7 times 2 should give us a 14. And over here on the other side of the plus sign, it's B sub 1 times B sub 2. So B sub 1 has a value of -4 and B sub 2 has a value of -1, correct? So that would give us a +4. So let's pull up the next step. So 7 times 2 is 14, -4 times -1 is a 4, and we should get an answer of 18, which is a scalar quantity, correct? Which is a numerical value, a scalar term. Next is W dot V. So this time W is our first vector and it's the dot product with V. V comes in the second position here. So let's follow the process. It's the same thing. So we have, however, 2 times 7, all right? Because W is now placed in position 1, but they're treating its components as A1 and A2. It doesn't matter. It will not make a difference to the answer. So the A component for W is 2 and the A component for V is 7. So 2 times 7 plus -1 times -4. B sub 1 times B sub 2 should give us 14 plus 4, which is equal to 18. So it doesn't matter which vector comes first. If it's a case of dot product, you will end up with the same answer. The same scalar quantity in this case was 18. The next one is the dot product of the same vector. So W dot W. When we perform that operation, it's 2 times 2, correct? So we are now focusing on the components of the same vector. So A sub 1 times A sub 1 is what happens now. So 2 times 2 is a 4 plus -1 times -1 is a +1. We end up with 4 plus 1, which is equal to 5. All right. Now we will see later on that when we find the dot product of the same vector, the result will be its magnitude. But this was an example of applying the formula to find dot products on real vectors. We will now learn about the properties of the dot product. If U, V, and W are vectors and C is a scalar quantity, then number 1, the dot product of U and V will be equal to the dot product of V and U. This is similar to the commutative property that we learned previously. Number 2 is the dot product of U and the result of adding two vectors V and W. So within brackets here we have V and W being added. That has to be performed first. It's within the brackets. That will result in a vector. And then we find the dot product of the resulting vector with U. When we perform that operation, it would be the same as finding the dot product of U and V and adding to it the dot product of U and W. Next, number 3 is when we find the dot product of a non-zero vector and a zero vector. The result is 0. Now this 0, the answer 0 on the right hand side is a scalar quantity. That's just a number 0. Whereas on the left hand side, the 0 in bold means it is a zero vector. So this means the dot product of the zero vector and the non-zero vector V. Number 4 is the dot product of the same vector, v dot v. Now, the result is the magnitude of the vector squared. That's what you get when you find a dot product of the same vector. Number 5 is when we multiply a vector by a scalar quantity and then find the dot product with another vector. So within brackets we have C and then dot v, which is equal to, or which is the same as taking the dot product of the two vectors first and then multiplying it by the scalar quantity c. So these are some of the properties of the dot product that we might have to use, or we may have to identify and use accordingly. Now we will look at an alternative formula for the dot product which uses a trigonometric function. It says if v and w are two non-zero vectors and theta is the smallest non-negative angle between them, then v dot w is given by the formula the magnitude of v multiplied by the magnitude of w times cos of theta. So this formula helps us find the dot product of two vectors as well. Now, using the alternative formula that we just learned, we can find the angle between two vectors. What was the alternative formula again? It was v dot w is equal to the magnitude of v multiplied by the magnitude of w times cos of theta. So if we have to find the measure of theta here, all we need to do is solve this equation for cos of theta and then finding theta using the rules of trigonometry that we learned. So we need to isolate cos of theta. In order to do that, we'll divide both sides by the magnitude of v and the magnitude of w, and we will end up with v dot w divided by magnitude of v times the magnitude of w. That's going to give us cos of theta isolated on one side, and next we can find the arc cos of whatever this number evaluates to be and find the measure of theta. So it says if v and w are two non-zero vectors and theta is the smallest non-negative angle between v and w, then cos of theta will be equal to v dot w divided by the magnitude of v multiplied by the magnitude of w, and then we find the angle measure theta by taking the arc cos of this entire expression given. All right? Here's an example of finding the angle between two vectors. The two vectors given to us is v equals 4i minus 3j and w equals I plus 2j. So we have to use the formula that we learned to find the angle between the two vectors. Let's pull up the formula first. Cos of theta equals the dot product of v and w divided by the magnitude of v and the magnitude of w. So here we not only have to calculate the dot product, but we also have to find the magnitudes of v and w. We have v dot w is written as 4i minus 3j dot I plus 2j, and then the magnitude of v will be calculated using the formula square root over a squared plus b squared. All right, so a for the first one, let's do this here. A has a value of 4 and b has a value of negative 3 for vector v, whereas for vector w, a has a value of 1 and b has a value of positive 2. So we have to make sure we plug in the values correctly. So we have 4 squared plus negative 3 squared for the magnitude of v. We have to find the square root of that, of course. And then for w, the magnitude is square root over 1 squared plus 2 squared. All right. So when we perform this calculation, let's see, 4i minus 3j would give us 4 times 1, correct? A1 times A2. So this is our A and this is 1 is our, here, let's A1, and this is A2. So A2 is a 1 and A1 is a 4. As far as B1 and B2 are concerned, B sub 1 equals negative 3 and B sub 2 is a positive 2, correct? So make sure again you plug in the values correctly. It's 4 times 1, A1 times A2, 4 times 1, plus negative 3 times positive 2 gives us 4 minus 6, correct? 4 plus minus 6 gives us a negative 2, and then in the denominator we end up with square root over 25 times square root over 5, which gives us square root over 125. The angle between the vectors therefore would be theta equals r cos of negative 2 divided by square root over 125, which gives us an answer of 100.3 degrees when we use our calculators. So this value here, negative 2 divided by square root over 125, is essentially a cosine ratio for theta. So once we get that ratio, we can find the theta using our calculators. All right, and that's what we did. Now let's learn about parallel and orthogonal vectors. Two vectors are parallel when the angle theta between the vectors is 0 degrees or 180 degrees. If theta is 0 degrees, the vectors point in the same direction. As in this picture here, we see two vectors, one is v, the other one is w. They are of different magnitudes, but they are pointing in the same direction. That means the angle between the two vectors is 0 degrees, all right? As far as 180 degrees is concerned, the vectors, even though they may be of different magnitude, if they are pointing in the diametrically opposite direction, one is going east, the other one is going directly west, then that means their angle between them is 180 degrees. In both cases, they are parallel vectors. Therefore, when the angle between the two vectors is either 0 degrees or 180 degrees, they would be considered parallel vectors. The next is orthogonal vectors. Two vectors are orthogonal when the angle between the vectors is 90 degrees. So we have one vector v going up and the other vector w is perpendicular to it, is running at 90 degrees to the vector v. In that case, we consider the vectors to be orthogonal. All right? Now there's a way to determine whether two vectors are orthogonal or not, that is, whether they run perpendicular to each other. The example here asks, are the vectors v equals 2i plus 3j and w equals 6i minus 4j orthogonal or not? Now the way to determine that is by taking the dot product of the two vectors. If the answer is a 0, that'll tell us that the two vectors are orthogonal. So let's go through the process of finding their dot product and then checking if the answer is 0. So the vectors are orthogonal if their dot product is 0. So keeping that in mind, let's find the dot product. V dot W equals 2 times 6, A1 times A2, therefore 2 times 6 plus 3 times negative 4, B sub 1 times B sub 2. B sub 2 is negative 4 in this case, correct? And when we complete the dot product, 2 times 6 is 12, 3 times negative 4 is negative 12. Therefore, 12 minus 12 gives us a 0. So we can conclude that the vectors are orthogonal because their dot product is 0. All right?